So we've learned how to round off to one figure or two figures or three figures, but let's see now where we need to use this and how it's related to what's called the degree of accuracy. When we measure something, the degree of accuracy to which we can or should give the result can vary considerably. It depends on a lot of things. For example, it depends on how good our measuring tool is, doesn't it? For example, if I'm trying to find the diameter of this bolt, if I'm just measuring that with an ordinary ruler, obviously because the ruler is not that fine and the measurements are not that fine, and also it's very hard to measure across and estimate the diameter, I could probably only measure it at best to 1 millimeter. But there are instruments, this one's called calipers, that enable you to measure it to, it says here, 0.462 centimeters, which is 4.62 millimeters. In other words, if we were to put this bolt into the gap here and use it carefully, we'd be able to measure the diameter of the bolt to the nearest 1/100th of a millimeter. So this tool enables us to measure it to 1/100th of a millimeter. This one probably only to the nearest millimeter. So that's an example of how a measuring tool can affect the degree of accuracy to which we can give a measurement. Another thing it depends on is how accurately the thing we're measuring has been made, or how uniform it is, or how square it is. For example, here's a picture very much reduced of a piece of A4 paper. But A4 paper is cut out pretty accurately, and therefore we can measure its length and its width quite accurately. However, if we're trying to measure the length and width of this, which is like a paper mache piece of paper, obviously the length varies and we'd be hard pressed to give an accurate length, maybe even just to the nearest centimetre is the best we could do. It also depends on how well we measure, how good we are at measuring. We as humans can make lots of errors when we're measuring. Here's just a couple of examples. If we were trying to measure the length of this rectangle with a ruler, we need to make sure we're directly above the ruler and lining it up with the edge of the rectangle. If we're looking a bit from the side, we can get a different measurement as it's indicated here. This is the correct one. These would be incorrect. That's called the error of parallax. Likewise, if we're trying to measure how much liquid is in this measuring cylinder, we need to know that we need to look at the bottom of the curved surface of the top, which is called the meniscus. If we're measuring at the top, we'll be making an error, and therefore our giving of the volume or the capacity of that's in that measuring cylinder would be quite inaccurate. Another thing it depends on is who's going to use the measurement or what it will be used for. The audience, who we're telling it to. For example, you may know that in the first game at the Adelaide Oval, records of attendance showed there was 50,397. But if I was telling a friend roughly how many people are at the game, I'd round that off and say, oh, there were about 50,000 there, and rounding it therefore to the nearest 1,000, 50,000. But if we wanted to determine in the future whether this record is going to be broken, we'd always have to refer to this figure, wouldn't we? So we need to tell that to the nearest unit or to the nearest person. That's what we'd have to compare any other attendances with. Another example of who the measurement will be used by, or the audience, is this. If you're going to have a bedroom built and you're trying to give a friend an idea of the size of the room, you might say that is about 5 metres by 3 metres. In other words, rounding it off to the nearest metre or to just one figure. If you're working out how much carpet was needed to carpet the whole room, then to tell the person who's going to carpet it how much you need, you'd probably need to tell the person to the nearest 0.1 of a metre. 0.1 of a metre is to the nearest 10 centimetres. In other words, to two figures. Now, if you're telling a builder who has to build the room, builders claim that they can build it accurately to the nearest millimetre. So 5.115 metres by 3.310 metres is telling the builder to the nearest millimetre, or 3, or actually they're 4 figures, isn't it, not 3? So here's another example. Say you were measuring the height of a tree. Now, if someone told you it's 5.3452334 metres, you will say that's a ridiculous degree of accuracy. You could never measure a height of a tree to that accuracy. Why not? Because maybe the ground's a bit unlevel here. Maybe the tree is moving in the wind. Maybe it's a bit hard to determine which is the actually highest leaf of the tree. This would be a ridiculous degree of accuracy. Even if they gave it to 5.35, that is saying you can measure it to the nearest 1 centimetre. I don't think you can measure the height of a tree to 1 centimetre for the same reasons I just gave a minute ago. So that one is too accurate. Probably to the nearest 10 centimetres would be a reasonable degree of accuracy. On the other hand, if you're measuring the heights of different species of trees in a forest, so we've got different types of trees here, then probably if they told you it was 12.8 metres, you say, well, that's 12 metres and 80 centimetres, rounded off to the nearest 10 centimetres. It's a bit too accurate. We don't really need it to that accuracy. Probably just, in this case, to the nearest metre would be sufficient. 12.8 rounded off to 13 metres is the height of this tree here, say. This one we might say is 2 metres. This one we might say is 3 metres. This species here is 6 metres, and this one about 18 metres. In other words, all the time we're rounding off to the nearest metre, and that would be sufficient degree of accuracy in that situation. On a smaller scale, measuring the heights of growing wheat in an experimental field, if the experimentalist told you this, now that's a bit ridiculous, I know, you could never measure it to that. Well, you might be able to get a measuring instrument that could measure one blade of this wheat to that accuracy, but that is a ridiculous degree of accuracy. The experimentalist might just be trying to get a general idea of how high the wheat is after, say, 10 days. So probably that, or to the nearest centimetre, would again be a suitable degree of accuracy. Now, something else happens when we come to combine measurements. If I'm trying to find the area of this drawn rectangle, I need to measure its length and its width. Now, if I did that with a ruler, let's see what happens. If I look at it carefully, I reckon I could probably draw it to the nearest millimetre, or measure it to the nearest millimetre. So in measuring its length and its width, to the nearest millimetre is a sensible degree of accuracy for the length. So if I measure the length, and I've done this, I estimate that to be about 114 to the nearest millimetre, and the width I measured a while ago to be 52 millimetres. To the nearest millimetre is probably the best that we can do. Now, we don't need our ruler anymore. Let's now think about how we'd calculate the area of the drawn rectangle. I've measured its length to be this and its width to be this. I'm going to calculate its area by timesing its length by its width. So 114 times 52 is 5928 millimetres squared. Now I'm trying to decide whether that's a sensible degree of accuracy. Well, if I could be 100% sure that these numbers were right, exactly right, then it would be. But you probably noticed when I was measuring before, you might have disagreed with me with the length and the width. But let's just see what happened if the width was a little bit different. If I was 1 millimetre off, say, if maybe it was 51 millimetres, then what would the area be then? Length times width, now is 114 times 51. So if I was just 1 millimetre off in the width, I'd get this number, a smaller area. If I was 1 millimetre off the other way, then the area that I would get would be 114, the length, times the width, in this case 6042 millimetres. So you can see just a small bit being off in these measurements makes quite a difference to the area. So really, because we're not 100% sure of these measurements, I don't think I can say that the area is exactly this. I probably should round it off to 5900, round it off to 2 figures. We call them 2 significant figures or 2 significant numbers. And that's probably the best that I can do. In fact, there's a good little rule to remember that we should only give our answer to the number of significant figures of the least accurate data, no more than that. So this is our least accurate data. The width was given to 2 figures. So we should give our answer to no more than 2 figures. Just summarising that, we've got a rule to use. When combining measurements, generally round to no more significant figures than the number of significant figures in the least accurate data that you are using. And another example, slightly different because this time this shows you what needs to be done if one measurement is quite accurate. Find the speed of the car if a car odometer showed that a car travelling 420.6 kilometres. That's pretty accurate. But the other one, time estimated the driver to be 5 hours. Now he's only estimated that. That could be quite out, is what we're suggesting here. So if I worked out the speed, taking this figure and this figure, we work out speed by dividing the distance by the time. So it's 420 divided by 5. And that gives, if you use your calculator, 84.12 kilometres per hour. But because we're not sure of this number here, we can't leave this as an answer. This is far too accurate, given that this one might be quite a bit out. Now, the guys that estimated this to be 5, anything, it could have been 4.5. 4.5 would have been rounded up to 5. So if I divide 420.6 by 4.5, you can see actually you get quite a different answer for the speed. Now much bigger speed, 93.466. It could have been up to almost 5.5. Let's say 5.4 and see what happens. If we divide the distance now by 5.4, which would have been rounded down to 5, now we get 77.88. You can see you get quite a variety of answers, variation in the answers, if one figure is not that accurate. So now, what do you think would be the best estimate we could give for the speed? We can't give it to this accuracy, of course. I think probably we could only round it off to one figure. It's about 80 kilometres per hour. This is accurate to one figure, so we probably should only give our answer to one figure. So there's an idea of how we use rounding and have to consider the degree of accuracy before we give our answer.